Welcome, welcome. Thank you for joining us for Class 2 as we build up on our knowledge of linear functions to include systems of equations, inequalities, absolute value inequalities. Are you ready? Let's begin. Anytime I solve two linear equations, the intersection points are the solutions of those equations. So I've got three cases that are possible when I look at them visually or graphically. The lines could be parallel, in which case they don't intersect at all, which means there are no real solutions to that equation. I've got two distinct lines, they're parallel, and there's no intersection. So if I need to find no real solutions, I know I'm looking for a parallel line. On the other hand, I could have literally the same line. So if my second line was not distinct and it lied exactly on top of the first line, there would be infinitely many solutions, that is, real solutions. Think about it. Every point, and there are infinitely many points on the line, would be the same between the two lines. And lastly, I could have two lines that have different slopes and they intersect in one point. Two lines will intersect in exactly one point. So there's going to be one real solution in the case that my slopes are different. So these are our three scenarios and what we want to be on the lookout for in these cases. So in the parallel case, let's look at that in standard form for a second. Suppose I had 5x plus 5y equals 10. A parallel line might be something like 5x plus 5y, the same ratio of the a to b coefficients, equals 20, a different c value. They would be separate lines but parallel. That would have no real solutions. In y equals mx plus b format, that might look something like y equals, say, 3x minus 3. Or a parallel line to that would be y equals 3x. Different y-intercepts, so they're separate lines, but they have the same slope. Therefore, they're parallel lines. So that's what we'd be looking for as examples of no real solutions for a system of linear equations. What about the case where we have infinitely many solutions? Let's start again with that 5x plus 5y equals 10. Well, 5x plus 5y again equals 10 would answer it, but what about 2x plus 2y equals 4? Is that the same equation? The answer is yes, it is. If I multiply this by 5 halves on both sides, I would essentially end up with exactly the equation on top. Therefore, they're exactly the same, and this would be an example in standard form of infinitely many solutions. They are the same line, effectively. On the other hand, what if the slopes are different in standard form? 5x minus 5y equals 10. And I have another line that might be, say, 5x plus 5y equals 10. Or I could have 3x plus 4y equals, well, we could say 10 again. That doesn't really matter so much here. These slopes are different. The ratios of plus 5 to minus 5, the a's to b's, is different than plus 5 to plus 5. The first example is a positively sloped line. The second example is a negatively sloped line, just kind of like our picture. And of course, the point of intersection between will be the solution of two equations. Likewise, 3 and 4 is a completely different ratio altogether, thus not parallel to any of the other lines, and would also be an example of one real solution. Anytime the slopes are not the same, you must have one real solution between the lines. How do we go about solving system of equations? There are two basic methodologies: elimination and substitution. In either case, the objective is to take the two equations and two variables, eliminate one variable in your first step to end up with one equation, one variable, solve for that, and then plug that result back into the original equation, the other one, to find the value for the other variable. Let's see how that's done with elimination. In this case, I see two equations in standard form. Elimination works very well when the format of the equations are the same. And that's typically when they're in standard form, as you'll often see on the exam. So sometimes there's a real quick elimination, like in this case. I simply add the second equation to the first equation. 2x plus 4x is 6x, plus 3y plus minus 3y is essentially 0y. That cancels. And 7 plus negative 1 is 7 minus 1 is 6. So 6x equals 6. X equals 1. And I've solved for the variable x. Now I can plug that back into the original equations, one of the original equations, and solve for y. So 2 times 1 plus, substituting 1 for x, plus 3y equals 7. So I'm going to subtract the 2 times 1, or 2 from both sides. 3y equals 5. Y equals 5/3. My solution is x 1, y 5/3. This would be the point of intersection between the two lines in these equations. What about the other method, substitution? How would we go about solving by substitution? Well, substitution works effectively when the equations are in different format. Notice our top equation is in y equals mx plus b format. The second equation is in standard form. In this case, I'm not going to bother putting one into the other format to make them the same. I'm just simply going to substitute. I've already solved for one variable, y, in this case, in one of the equations, and that would be the objective. If you haven't solved for the variable, solve for one variable. And then I'm going to plug that variable back into y in the second equation, which would be 2x plus 1. So when I do that, I get x plus y is really x plus 2x plus 1. By the way, when you substitute in, always put it in parentheses in case you're distributing. That way you'll always multiply it out correctly and not make a mistake. In theory, at least. So now that simply distributes to 2x plus 1 because the coefficient is 1 in the parentheses. So x plus 2x is 3x plus 1 equals negative 2. 3x equals negative 3. X equals negative 1. Now I can take that and plug back into my equation. Y, we know, equals 2 times x, which is negative 1, plus 1. That's negative 2 plus 1. Y equals negative 1. Here, the intersection point between the two lines is going to be negative 1, comma, negative 1. That is our solution to that system of equations. Let's take a look at a more challenging case where the two equations don't eliminate and tidy up as quickly or easily as our first examples. Now remember, the SAT is designed for questions to be answered in about 30 seconds. So usually there is a way to tidy them up pretty quickly. But in this case there isn't. So let's go through that. I've got 5 and 3 as coefficients of x, and 4 and 9 as my coefficients of y. None of those are nice multiples of each other that I could easily sort of eliminate or work through. So I'm going to have to scale both equations. I'm going to eliminate on x's. I could do it either way, x's or y's, but I'm going to choose x's. And I'm going to multiply the 5 by 3, the coefficient of the other x. And I'm going to multiply the 3 by the 5, the alternate coefficient, which is going to give me 15x for both of them. And then I'm going to subtract one equation from the other. So effectively, I get 15x plus 3 times 4 is 12y equals minus 30 times 3 is minus 90. And in my second equation, I will get minus 15x. And minus 5 times minus 90 is plus 45y. And minus 5 times minus 18 is plus 90. So what does that work out when I add the equations together? I eliminate my x's. I get 12 plus 45 is 57y equals minus 90 plus 90 is 0, which means y equals 0. Okay? So if y equals 0, I can plug back into the other equation and say 5x plus 4 times 0 equals minus 30. 5x equals minus 30. X equals minus 6. My solution point is minus 6, comma 0. Well, that wasn't too bad for what was a slightly ugly scaled elimination method up front. Let's tackle this same system of two equations by substitution. It's a little more complicated than our previous cases because we don't have one equation solved for y or solved for a single variable. We have to do that up front. So I could take the first equation, for example, and try to solve for x. Let's say 5x plus 4y equals negative 30. So I know 5x equals minus 30 minus 4y. Divide through by 5. X equals minus 30/5 minus 4/5 y. And that in turn equals minus 6 minus 4/5 y. I'm going to substitute that back into my second equation for x. So now in the second equation, 3x becomes, I will substitute minus 6 minus 4/5 y. And I continue the rest of the equation is minus 9y equals minus 18. Now I'm going to distribute minus 18 minus 12/5 y minus 9y equals minus 18. Right away I can see the solution now is going to be y equals 0. The 18s or negative 18s cancel, and minus 12/5 y minus 45/5 y, which is a common denominator, will be minus 57 over 5y equals 0. Don't really care what that coefficient is. I didn't really need to worry about that complicated, messy math there, because ultimately I'll divide through by both sides, and the answer will simply be y equals 0. That's exactly the same result we got in our elimination example. So the two work out, and then I would plug back in and find my x value and get the same solution. So slightly messier substitution and elimination examples, but now you've seen examples and can hopefully do it yourself if you run into that complication on the exam. Sometimes on the exam, we'll see a problem that presents a system of two linear equations in standard form in this case. 10 equals ax plus by, and we're told a and b are constants or coefficients. The second equation is 5 equals 2x plus 3y. The question is not solve for x or y. Don't solve the system. The question is what values of those constants a and b, or in this case a plus b, make the equations true for all real x. There's an alternative version that it's never true for any real x or real y in this case. Well, what has to be done to make that happen? In this case, we actually need the equations to be exactly the same. So I do see a similarity in equations here. If I multiply the bottom equation by 2, I'll get my constants on the left side to be exactly the same, and that's good. I need that to happen. And on the right side, 2 times my 2x is 4x, and 2 times my 3y becomes 6y. I need the 4x plus y to match the ax plus by. I need those to be the same. Only then will the equations be the same, and no matter what x and y are as real values, the equations will hold true. So in that case, I'm really solving for the coefficients. I need the a to equal the 4, the two coefficients of x. I need the b to equal the 6. They're the two coefficients of y. So b equals 6. Well, that was pretty simple. Those are the solutions that make the two equations true and solve for the constants such that for any real x and any real y, this system is always true. And they're asking for, in this case, a plus b, so that's simply 4 plus 6. The correct answer here would be 10. Notice that's slightly different than solving for the system of equations. You can learn more about linear solve for the constant problems in the How to Solve sections for the appropriate topics on math. System of linear equation problems often present in word problems. There are a few classic cases. Let's take a look at one of them that deals with prices and amounts. The school that Lisa goes to is selling tickets to the annual talent show. On the first day of ticket sales, the school sold 4 senior tickets and 5 student tickets for a total of $102. So we typically start with a price and amount of one group or item and a price and amount of another group and item. In this case, we've got 4 senior citizens. So let's call that 4C, the number times the price. We don't know the price. We'll call that C. And 5 student tickets for a total of $102. So that's going to be plus the price and amount of student tickets. Well, there are 5 students, and we'll call the price of a student ticket S. We don't know that, okay? And in total, we know that equals $102. Well, if we keep going, the school took in $126 on the second day by selling 7 senior citizen tickets and 5 student tickets. So we have a second equation here. We can say 7 senior citizens times the price of a senior citizen ticket plus 5 student tickets, again, times the price of student tickets, equals, in this case, $126. Now I have 2 equations in standard form, which often cases means I want to solve by elimination. I can do that because I can see right away if I subtract the second equation from the first, my s's will cancel as variables. So I'll get 4c minus 7c becomes minus 3c. 5s minus 5s is 0. And that equals 102 minus 126, which is minus 24. I'm going to divide through by negative 3. C equals $8. So the price of a senior citizen ticket is $8. What's the price of a student ticket? Well, I'm going to plug that back into the equation. So 4 times C, which is 8, plus 5 times S, or student ticket price, must equal $102. Well, that's 32 plus 5S equals 102. Let's subtract 32 from both sides. 5S equals 102 minus 32 is 70. S equals 70 divided by 5, or $14. So the price of a senior citizen ticket is $8. The price of one student ticket is $14. And that's how we answered these types of problems through a system of linear equations. Distance equals rate times time problems are another classic case of systems of linear equations. Almost always, they present as 2 legs of a journey. You have problems where somebody goes from point A to point B and then returns back to point A. Or you might have 2 parties that are apart, maybe 2 trains, leave from 2 separate cities and meet somewhere in between. You might have 2 separate legs of the same group on the same journey, leg 1 and leg 2. You could have one group leaves first, the other group or party leaves afterward and catches up at some point to the first party. And you could have parties leaving the same point and going in different directions, getting a further and further distance apart. Regardless of these few typical distance equals rate times time scenarios, they always have 2 legs to the journey, which means you have 2 distance equals rate times equations to set up, and possibly a total distance rate times time equation to help you work through the systems of equations. So let's look at this example. As Sally rides her bicycle 5 miles from her house to the beach in 30 minutes and then returns at 5 miles per hour, what is her average speed over the entire trip? Okay, this is the first scenario where Sally's riding to one point and then returning over the same distance. That's one of the key assumptions here. It's the same distance back and forth. So let's set up equation 1. Distance equals rate times time. We know her distance is 5 miles, and that should equal her rate times her time. We know her time's in 30 minutes. We want to make that consistent over the course of the problem. So we use hours here. I'm going to convert 30 minutes to half an hour. So the time is half an hour, and we don't know her rate. We're going to have to solve for that. Okay. On the return leg of the trip, we know she rides at a rate of 5 miles per hour. We don't know the time. That's an unknown, t. And we do know the distance. The distance must be the same back as it was going out, so that's going to be 5 miles. Now I have 2 equations, 2 variables, and I can go about solving for her speed over the entire trip. So a lot of students will look at this and they'll solve the first equation, for r equals 5 divided by 1/2, which is 2 times 5. R equals 10 miles per hour. So her speed on the first leg is 10 miles per hour. They notice that her speed given on the return leg is 5 miles per hour. So in a lot of cases, students will simply say 5 plus 10 divided by 2, 7.5. That's her average speed over the entire trip. That would be wrong. 7.5 miles per hour average is incorrect. You cannot use mathematical averages for rates, something students often miss on distance, rate, time problems. Why? Because you'd have to be going the same amount of time at those rates to do a mathematical average. In this case, more time is spent at the lower speed, 5 miles per hour, than at the higher speed. So the resulting rate will be weighted by that. So we should expect it to be a little less than 7.5 in this case. Let's run the numbers and find out. We do know that we can create a total equation for distance equals rate times time. And the total distance we know is 5 plus 5. It's 10 miles back and forth. And we have some average rate. We don't know that. Let's keep that as the unknown variable. And now we do know the time. We could solve for t in that second equation. The time equals 5 miles divided by 5 miles per hour, which is simply 1 hour. So t equals 1. We can add our times. We could not add our rates, but we can add our times. That's 1/2 plus the 1 equals 3/2 or 1.5 hours. Now I can solve for r average in my total equation. The total rate or average over the entire course, over the entire trip, is 10 divided by 3/2 or 6 2/3 miles per hour. It was, in fact, a bit less than the 7.5 miles per hour. So that makes common sense. We're weighted toward the slower speed where Sally spent more time on that leg of the journey. So it pays to get to know a lot of these distance equals rate times time variations and a lot of these systems of equation word problems variations. I would spend some time practicing, but these are some of the basics and the issues you might want to look out for. Up until this point, we've only been looking at equations. But what if one side is not equivalent to the other side? We have an inequality as opposed to an equation. For example, 2x minus 5 is greater than 10. Well, generally, we solve this the same way we would an equation. I'm going to add 5 to both sides to get rid of the minus 5 on the same side as my x, leaving me 2x is greater than 10 plus 5, which is 15. Okay? And then I would divide through by 2, the coefficient of x on both sides, to get rid of that and isolate my x, which is greater than 15/2 or 7.5. Okay, that's pretty easy. Our inequalities so far look like they are the same as solving equations. But wait a second, there's one major difference you need to be aware of for the exam. What if I had the following inequality, 5 minus 2x is greater than 10, and I began solving it much the same way. Subtract 5 from both sides. I'll get minus 2x is greater than 10 minus 5, which is 5. And I'll divide through by the coefficient of x, which is minus 2 in this case. And that isolates my x. But the key for an inequality is I must switch the direction of the inequality. X is now less than minus 5/2. So when we multiply or divide by a negative, we must switch the direction of the inequality. That's one key difference between inequalities and equations. Many of you might know that already, but it's so important it's worth emphasizing again. Likewise, if we take the reciprocal of both sides of an inequality, you must switch the direction of the inequality. That's one students don't appreciate in most cases. So how do we show that? Like, why is that really the case? Well, I could solve this a different way. I didn't have to divide by the coefficient. I could have just added 2x to both sides. I would have gone 5 is greater than 10 plus 2x. And then I would have subtracted 10 from both sides. 5 minus 10, which is minus 5, is greater than or equal to 2x. And then I divide by 2, no problem, because I'm not dividing or multiplying both sides by a negative. And simply x is less than minus 5/2. This is the same as this. X is less than minus 5/2. Here I solved it a different way without dividing by negative. So if I did not switch the direction of my inequality when I divided by negative on both sides, I would have been wrong. Let's extend our discussion of inequalities to compound inequalities, which you're more likely to see on the exam. In this case, I've got 2x minus 6 is less than 10, and 2x minus 6 is greater than negative 2. I have two inequalities connected by an AND condition, which means both parts have to be true. Alternatively, I've got two inequalities connected by an OR condition, which means one part has to be true only for the whole statement to be true. So let's take a look at these. We can always solve our compound inequalities as separate inequalities if we choose to, whether it's an AND or an OR statement. So let's go ahead and do that in this case. 2x minus 6 is less than 10. That means 2x is less than 10 plus 6 or 16. Divide through by 2. X is less than 8. On the second one, 2x minus 6 is greater than negative 2. So add 6 to both sides. 2x is greater than plus 4. Okay, divide through by 2. X is greater than 2. These are my two solutions. X is less than 8 and x is greater than 2. Note, I can combine these with my AND condition into one essentially three-way inequality. X is less than 8 and greater than 2. You'll often see this the case. I have a three-way inequality, okay? And by the way, we can graph that too on a number line. That would look something like at 8 and at 2. We know x is between 2 and 8. So it's greater than 2. We use the open circle to indicate everything to the right, greater than, but not 2 itself. An open circle at 8 to indicate it's less than 8, so everything to the left on the number line, but not including 8. Okay? This is an interesting one because we could have actually solved this as one compound inequality in our format that we have right here. So what would that have looked like? For example, we could have set up 2x minus 6 is less than 10 and is greater than negative 2. And I could have gone ahead and kind of solved it as a three-way inequality with my linear expression, one variable, in the middle. I would have added 6 to both sides, so we're less than 16, 2x, and greater than adding 6 to both sides, 4, and I would have divided by 2, and figured x is less than 8 and greater than 2. The same answer we get above, okay? Let's try this out on the OR condition. If I solve the OR condition, again, I can always solve it as two separate inequalities. So that's 2x. I'm going to add 6 to both sides. 2x is greater than 16. Very similar to our last one because they are, in fact, the same inequalities or nearly the same inequality statements. And then I'll divide through by 2 on both sides. X is greater than 8. That's one solution for the first inequality. How about the second inequality? 2x minus 6 is less than or equal to negative 2. Add 6 to both sides. 2x is less than or equal to plus 4. Divide through by 2 again. X is less than or equal to 2. That's the solution for my second inequality. So these are my two solutions. What would that look like if I graphed that? That would be something like, again, I've got these points 2 and 8. And the first one, x is greater than 8. So I'd have an open circle at 8 and greater than. It's everything to the right of 8, but not including 8. X is less than or equal to negative 2. So in this case, I have an equal condition as well. Notice the less than or equal. In that case, I used a closed circle to indicate 2 is part of my solution set. And it's less than. It's everything to the left on the number line represents less than. Don't make that mistake. Sometimes students think minus 8 is greater than minus 6. No, it's not. It's to the left on the number line, therefore it's less. Okay? So this is what our graph looks like. Well, wait a second. This is very different than the graph we saw in the AND condition case, which looks like our typical sort of dumbbell, if you ever use that on weights. On the other hand, the OR condition generally graphs to an open in the middle. And why is that in the ends? Well, let's think about that. In my solution set, I'm essentially saying something to the right of 8. Let's call it 10 is a solution. But it's not an and condition, it's an or condition. So I'm either 10 or I'm something to the left of 2, which might be, say, 0, right? I only have to meet one condition. If I had an and condition on this graph with this inequality, the solution set would be no real solutions, because there's no way I can be 10 and be less than 2, or be 0 and be greater than 8. So we can see the or condition has this type of graph and looks a little differently. By the way, I cannot generally write this out as a three-way inequality like we do before. But nonetheless, we can solve our and conditions, or conditions, and graph them. What about absolute value equations? How do we solve those? Absolute value equations and inequalities. Well, what does the absolute value do? It takes a negative value and makes it positive. We denote the absolute value as whatever expression or value is in between these two vertical bars. If the value of x is positive, it stays positive. If it's negative, the absolute value makes it positive. So that means the absolute value of 2, in this case, would equal 2. That's one solution. X equals 2. But also, the absolute value of negative 2, the absolute value turns that positive to make it also equal 2. So another solution is x equals negative 2. Note, I always have a positive and a negative solution case for the absolute value. So, okay, what if x is a more complicated expression? Who says it has to be just simply one variable? What if I said absolute value, instead of just x, x minus 5 equals 2? How would we go about solving that? Well, again, we know x minus 5 could evaluate to the positive 2. So we set up our positive case solution. And by the way, we also know x minus 5 could equal the opposite of 2 in the absolute value, in which case our equation is also true because the negative 2 is converted to plus 2 in the absolute value symbols. So we have a positive and a negative case solution for every absolute value equation, right? We don't have an easy inverse like addition, subtraction, multiplication, division, or for positive values of x, taking the square root of the square, vice versa. We have to adjust for this positive and negative case. That's how we go about solving absolute values. So now I've removed the absolute value symbol by setting up the positive negative case, and that's the key. Now I can solve. Add 5 to both sides on the first one, and x equals 7. On the next one, add 5 to both sides again, and x equals minus 2 plus 5, which is 3. And those are the solutions to our absolute value equation. We set up our positive and negative case and solve. So that's how we would approach it algebraically. Many of you might have learned or say absolute value is a representation of distance, and it is. If we think about it, the distance between any 2 points on a number line, say my solution x and 5, the point 5 on the number line, we represent that distance as x minus 5. This absolute value equation is saying that distance is a distance of 2. So my solution point x is a distance of 2 from 5. Well, we know that's x equals 7. But also 2 in this direction, which would be 3. That's also a distance of 2 from 5. And in that case, I might get a negative result, but the absolute value of x minus 5 makes it a positive distance, and x equals 3 is also a solution. Note, I have the same solution points, but I'm interpreting my absolute value equation as a distance here. It's a distance that's 2 away from 5. This intuitive approach can help you quickly discern the solution points of an absolute value equation without having to use the algebra. But I caution you to be careful. As this equation gets a little more complex, it becomes more and more difficult very quickly to sort of intuitively interpret the absolute value as a distance function for most students. When solving absolute value equations, there are a couple important points that students should take notice of. For example, number 1, 2x plus 10 absolute value equals negative 5. What do we think of that? Well, right away, if you're attentive, That cannot be true. The absolute value is always positive. It takes a negative, makes it a positive, and keeps a positive positive. There is no way a positive can equal a negative value. So right away, we know that case would have no solutions. Secondly, what if I had minus 2 times absolute value x minus 5 plus 10 equals 20? A lot of students might try to jump right into the algebra and take a positive case and a negative case right here. They'll say minus 2 times x minus 5 plus 10 equals 20 and try to solve that. And then in the negative case, minus 2 times x minus 5 plus 10 equals negative 20. Be careful about that. The change in the positive and negative case does not apply to the other parts of the equation beyond the absolute value. So we can't be certain this is going to be correct. The correct approach should be to isolate the function, the absolute value function, and then apply your inverse operation, in the case of absolute value, a positive and negative solution case. So isolate your function first. As a general rule, whether your function is a square function, a trig function, any other type of function, you probably want to isolate that function first and then try to undo it to then solve for the variable. So how would we work that in this case? First things first, I would subtract 10 from both sides. And that would give me minus 2 times the absolute value x minus 5 equals 10. And then I'm going to divide through by negative 2 on both sides. And that isolates my absolute value expression on the left side. That equals negative 5. Well, right away I see again, just as we saw above, this will not work. It'll have no solutions. But the important point is here, only at this point when I've isolated absolute value by itself on one side can I apply my positive and negative case solution. Don't try to do it when other things are going on with the expression. What about absolute value inequalities? In this case, absolute value of x is less than 2. How does that work? Well, again, that means x, if we go with our positive and negative cases again, it means x is less than 2. It also means the x is less than the opposite of 2, but again, wait a second, if we're changing on an inequality the sign for our negative case, we have to switch the direction of our inequality. X is greater than negative 2. Absolute value inequalities are essentially the same as compound inequalities. So in this case, x is less than 2 and greater than negative 2. This is an AND condition. When my absolute value is less than, it's effectively an AND condition. And I could graph that as such. That gives us our typical at 2 and negative 2, our typical barbell type solution in between the 2 points. About x minus 5 is less than 2. Before we saw with the equations, I can interpret as a distance. Can I interpret this as a distance? Yeah, my solution, the distance between x and 5, because that distance is represented as x minus 5, the absolute value means it's in both directions, must be less than a distance of 2. So that means right away I can say from my center point of 5, I can go up to 2 to the right, but not 2 or further, and I can go down 2 to the left from 5, but not down 2 or further. So my solution right away, I can kind of eyeball this as a distance and interpret it as x is less than 7 and x is greater than 3. Again, I'm using the same distance interpretation I did on my absolute value equations. Let's solve algebraically my positive and negative case here. What do we get? X minus 5 is less than 2. That's my positive case. Pretty simple. I usually just take away the absolute value symbols. By the way, don't leave your absolute value symbols there for your positive and negative case. A lot of students do that. The whole point of generating a positive and negative case is to undo the absolute value function. Okay? Now, here's a very important point. if you didn't see it from the first example, on inequalities, my negative case must correspond to a change in the direction of my inequality symbol, as we learned when we multiply and divide through by negatives on inequalities. So in this case, x minus 5 is not less than -2. It becomes greater than -2. I've switched the direction of my inequality symbol. And by the way, I can write this again as a compound inequality here. X minus 5 is less than 2 and greater than -2. And I could solve it with that three-way inequality if I chose to. I'd add 5 to both sides. I get x is less than 2 plus 5, or 7, and x is greater than -2 plus 5, which is 3. Exactly what I expected from my intuitive interpretation as a distance. If you aren't comfortable with interpreting inequalities or absolute value inequalities as distance, don't worry about it too much. Just remember, you can always solve algebraically with your positive and negative case. Note, in our first two cases, the absolute value inequality was less than 2, or the fixed amount. That resulted in essentially a distance interpretation of my center point. All solutions were within some distance of that center point, which resulted in a compound inequality, which essentially put x in between two values like that. And the graph, as a result, was our standard barbell graph, where we had 2 points, and the intersection of inequalities between those 2 points was the solution set. And recall, that was our AND condition at play. But what happens if our inequality is greater than, or the absolute value is greater than the value? Say, absolute value of x minus 5 is greater than 2. How would we solve that? Well, on a distance interpretation, we'd interpret our solution as a distance greater than some amount away from a center point. In this case, greater than 2 away from 5, which would probably be x is greater than 7 and x is less than 3. Algebraically, we could go through and solve that and see if that's in fact the case. Let's try our positive and negative solution cases. That's x minus 5 is greater than 2 in this case, and x minus 5 is less than -2. So that means x is greater than 7, x is less than 3. Well, what exactly is that? We can't write that as a three-way inequality like our AND condition. Why? Because this is an OR condition. Think about the graph. This is our case where the solutions greater than some midpoint, 5, 2 greater away to the upside. That's 7, or not including 7, but greater than 7, so everything to the right is 7, and greater than a distance of 2 down from 5, which would be 3, everything less than 3. This was our OR condition. In other words, a point in the solution set here cannot also or and be in the solution set up here. It's one or the other. So the only way to make it true, a true statement, is with our OR condition. So notice the difference in graphs from the different inequality setups on absolute value inequalities. They do correspond to our compound inequalities, as we saw in the earlier lesson, but they're different. And again, you can recognize them as different cases with the less than and greater than symbols. Okay, so we just learned how to solve systems of equations where if they were distinct lines and unless they were parallel, always intersect at one point, which gives us one xy point solution for the system of equations, the two variables, whatever they might represent in a word problem or otherwise. How do we go about solving systems of linear inequalities? Well, in this case, it's going to be different. There is not just one point of intersection or one point solution. You're going to have an intersection of entire areas of solution sets. So you're essentially going to have infinitely many points within a region of intersection that's going to be your solution set for the inequality system. Let's take a look at that in this case. Suppose I had two slope-intercept y equals or greater than mx plus b type format inequalities. How would I go about solving it? Well, the first step is I'm going to look at my first equation, or I should say my first inequality, but I'm going to treat it like equation. Y equals 4x minus 3. I know how to graph that. That's going to be a y-intercept of negative 3. It's going to have a slope of 4, so I'm going to go over 1 in x and up 4 in y. Over 1, up 4, and I can graph that line. Now I'm going to be careful. It's actually not equals, it's greater than, which means the line itself, or the points on the line, are not included in my solution set. If that's the case, I'm going to use a dashed line for my graph to see the solutions here. Remember, the points on the line are not part of, but all the y points greater than that line, which is essentially everything above that line, are solutions to my inequality. Okay, see how that works for that inequality. Let's try the second inequality. Y is greater than or equal to negative 2x plus 3. So again, I'm going to graph the line as though it were an equation, because I know how to do that and visualize it fairly easily. Y equals minus 2x plus 3. That will have an intercept, a y-intercept of plus 3, and it's going to have a negative slope. So if I go over 1 in x, I'm going to go down 2 in y, and vice versa, and I can keep plotting those points out. Now in this case, notice greater than or equal to. The equal to indicates that points on the line are part of the solution set, which means I fill in a complete shaded line, not a dotted or dashed line. This is to indicate that the points on the line are also part of my solution set. Now, greater than, every y greater than or equal to that line is part of my solution set. Well, guess what? That's everything above the line. Y's are greater than that. So what is my final solution set? How would I look at this? Well, my final solution set is going to be the intersection of those two. It's going to be everything above the one line and everything above the other line, the intersection of the purple and green regions, which is effectively this region in here. That will be the area of my solution set. So you might ask, well, I see it intersects at 1, 1. That's pretty obvious from the graph. Is 1, 1 part of my solution set? The answer is no, it's not. It's only a solution to one of the inequalities, the greater than inequality, the dashed line. It's not part of the solution set. So it's not a solution to the system. So be careful of that. That intersection point in this case is not part of the solution set. If they were both greater than or equal to's, it would be. We can run a similar exercise on standard form inequalities as well. Note in this case we have two inequalities in standard form. I might begin by graphing the equations. X plus y equals 2. Well, how would I graph that? I'm going to plug in x equals 0. I know y equals 2 and x equals 0. And I'll plug in y equals 0 to get the x-intercept. X will equal 2 when y equals 0. I'll connect those points and I get the line for x plus y equals 2. But again, I want x plus y is greater than 2. I'm not going to convert it to y equals mx plus b format, but I can see y is going to be plus y is going to be greater than the rest of the expression. So that's greater than. That's going to be a dashed line. My solution does not include the dashed line, but every y greater than that is going to be in my solution set. So all y values above the dashed line. Okay, well, let's try that for the second inequality. 2x minus y, and let's suppose for a moment it equals 1, so I can graph that. Again, I might plug in 0 for x to get y. Y equals negative 1 in that case. So when x equals 0, y equals negative 1. And I can plug in 0 for y to get my x-intercept. So 2x equals 1. X will equal 1/2 when y equals 0. And I can begin to then graph the rest of that line. But again, I know it's an inequality and it's a greater than symbol here, so it's going to be a dashed line, just like the other one, not part of the solution set. Sorry, not the best dashed line, but did the best I could. And in this case, I know minus y is greater than. So really, if I added y to both sides, I would have y is less than. So the region I'm looking for is all y values below the pink dashed line. And I know my solution region is going to be, therefore, the intersection of the two. It's going to be below the pink dashed line and above the green dashed line, which is effectively this region right in here that I'm shading in light blue. Again, the intersection point and all points on the line will not be in this solution set. Okay? And if I wanted to find a particular point that's in the solution set, well, hopefully it's obvious graphically, but your more accurate way is to plug that point back in the two inequalities and check if that works. Systems of linear inequalities can also present as word problems. So, for example, the school needs to buy hardcover books and softcover books. Softcover books cost $10 per book, and hardcover volumes cost $30 per book. If the school buys no more than 20 books and can spend at most $500, which inequality represents the situation? So how do we find and set up the right inequality that reflects this word problem? Well, we again know we have the situation where we have price times the number of hardcover plus price times the number of softcover equals the total expenditure. So I'm going to say the price of the hardcover, which we're told is $30, times the number of hardcover books, let's define that variable as H, plus the price of the softcover, $10, times the number of softcover books, we don't know that, so let's call that variable S, must be at most 500. So what does that mean? That means it could be 500 equal to, but it can't be anything more. It has to be less than or equal to. So the correct inequality for the price and amount is 30H plus 10S is less than or equal to 500. We also have the equation for the total amount of books. We're told the school buys no more than 20 books. So the number of hardcover books they buy is H, plus the number of softcover books they buy is S. That's no more than 20. Can that be 20? Yes, it can be. Can it be more than 20? No, but it could be less. So again, this is going to be another less than or equal condition. It's going to be less than or equal to 20. Slightly different wording, but again, you have to translate the wording into the correct inequality. Less than, greater than, less than or equal to, or greater than equal to for the appropriate scenario and word problem. This is the answer that represents the system in the word problem. And that brings us to the end of Class 2 of Heart of Algebra. We've now completed all our linear function work and overview for Heart of Algebra. The next step is going to be nonlinear functions, advanced mathematics, quadratics, exponentials, etc. Are you ready?